Okay, which graph correctly shows how the pH and degree of dissociation and K of uric acid vary with dilution at constant temperature? Okay, so if you have a weak acid, okay, for example, I'm just giving you a simple example, ethanoic acid. When you have a weak acid and you add water, okay, add water, essentially the H plus concentration will fall. Okay, when you add water, H plus concentration will fall and pH will definitely increase, all right? But there's a cap to where pH can reach. pH will only increase up to 7 because that is the pH of water, right? It cannot become from acidic solution, you can't add water and becomes basic. So the max it can reach is actually 7. So this statement 1 is definitely true. Okay, this is actually true. Okay, let's look at 2. Okay, so maybe I do 3 first. When you add volume of water added, the Ka is increasing, but this is wrong. Okay, this is wrong. Why? Because Ka is only dependent on temperature, so adding water will not affect the Ka. Right, so 3 is out. Okay, let's see how dilution can affect the degree of dissociation. So I've written down the Ka of the weak acid, and you notice water is not part of the equation. So when you add water, essentially, how does it affect? Okay, so maybe you ask yourself, how does it affect? But adding water will actually decrease the concentration of the CH3CO minus H plus ions as well as the ethanoic acid, right? Will decrease the concentration of these. So say for example, hypothetically speaking, I just want to do some calculation so you can understand how it works. So say the concentration of all these are 1 mole per dm cube at equilibrium. So this is like 1 times 1 over 1, and that's my Ka. So I'm just to keep things simple. All right. So let me draw it out first. So what happens when you add water? Say you have a 1 dm cube, okay, but now you add another 1 dm cube of water, right? So we add another 1 dm cube of water, now the volume doubles and the concentration will half. So when the concentration half, these values will become half, half, and half. And this is what I call the reaction quotient, which I normally represented by Q. And actually this is equals to half. So which means now the equilibrium position have to shift because we know that Ka doesn't change, right? Or the Kc, Ka doesn't change. So the half must slowly gravitate towards 1. It must shift until it becomes 1, right? So for it to shift until it becomes 1, it means that the numerator must actually increase and the denominator will actually decrease. So what is really happening is for the numerator increase, it means the equilibrium is shifting to the right hand side. Okay, so equilibrium is shifting to the right hand side. So which means this, when I dilute it by adding water, in fact the equilibrium shifts to the right, which means the degree of dissociation actually increases. Right, so over here you can see that when water is added, the degree of dissociation is actually increasing, all right, until it becomes 1. Right, so that's why this is actually correct. So the answer is 1 and 2.